I can see also, it's very nice to see the effective, the cumulative effective mass participation factor. What does it mean? This is the mass that participate in each frequency and in each axis. So you can see from, let's say, Y point of view, in Y direction, it's starting to behave, to resonate only from this frequency. But in X, it's starting from here. Okay? So you can have an idea also on different axes and different mass participation. Okay, let's go back here. So we have seen resonant frequencies analysis, quick and easy, because if you have set up something already in a static analysis, it's very easy to drag and drop some boundary condition. The buckling load factor is very critical to understand in structures, in compressive behavior, which is the load factor that we have to be aware in comparison to the static load factor. Okay, or the factor of safety. And it's based on model analysis. Let's go on. Now I would like to use another example, more on the structural side, more on structures, to show you the case manager. Let me go to simulation. So let's open the, I think this is, okay. So here I have basically, okay, we have some problems with the line, but please remember that this session will be recorded and you will find the link to the recording after some days when it's finished. If you are not receiving the recording, please let me know, email me so I can give you back the link to the recording. Okay, let's go back to this. In this case, I have a structure, a steel structure. It's made by the Wellman profiles. Maybe you already know that we have a specific application, a specific portion of the software to build something like that. So you can see 3D sketches or just sketches and a profile, a steel profile applied. Okay. What does it mean? It's automatically detected from the software, and when you are doing an analysis, it will be treated like a beam mesh. I can show you here. Basically. Okay, this is the beam mesh. Okay, it's a very simple mesh, it's very quick to use, and it will give you the first information about load diagrams, load cases, and so on. Okay, this is the static analysis. So I can just add, for example, the gravity, I can add the self-weight, I can add, for example, the weight by the snow or the weight by the wind, and so on, all together. And I can activate a load case scenario. I can show you here more. Okay. So here, what's happening? Basically, you have all together all the loads that you have defined, and you can define the primary load cases. For example, here the gravity, for example, the snow, the wind, and so on. And you can combine it with a specific linear combination. So a coefficient multiplied by the load that you have to calculate. And for each calculation, I can also add results. Here I can add a sensor, and with the sensor I can track, for example, distress in a point or displacement or what you need. And again, from report point of view, you can see all the report. Let's go to the Word file here. You can have all this kind of information reported on a Word file for each combination that we are using. So, okay. So what does it mean? It means that in just only one case, you have all these combinations. So it's very useful, and you can also import from a CSV file. So if you have just a software, there are software on the market to import this kind of combination, you can just use it. Okay. Let's go forward because we are really late. Okay. So here again, we have only one analysis with all these kind of combinations all together, and the automatic report generation for all this kind of case. Parametric optimization, this is a very important tool in simulation professional. Let me show you how it works. Okay. So here what I have. Okay, what I have here, it's a simple heatsink. I am designing the heatsink, and I'm concerned about the fins, which is the correct dimension to support the heat from the LEDs. And of course, I don't have, let's say, a trivial solution, because, for example, if I'm putting too much fins, they are blocking the flow of the air. If they are too few, they are not dissipating. So it's not trivial. And of course also the geometry is not trivial. So what I can do, I can just have from the sketch of the single, you can see here. So I can have just the parameters of the geometry that I want to refine. I can define a study, a thermal study in this case. I will run it just to show you some results. Again, this is very easy to use and quick. I have just some heat flux from the base and the convection to the air. Okay, very simple to do it. And which are the results? The temperature, of course, and for example, the heat flux. So I can see how is going on about the heat flux. Okay. Okay, now I'm changing to a design study. What does it mean? Here I can input that I have, let me zoom it, okay. I can just define, for example, parameters. So for example, the depth of the fin, the height, the number, or the thickness, and I can put a continuous range, okay? I have also constraints. In this situation, for example, I can just, I can use multiple constraints as well, but in this case I have just one constraint that I want to have the temperature from the thermal analysis less than this value, because I know, for example, that the LED will not continue to work after this value. And of course I want to minimize the mass. Most of the time it's like that. Okay, how it's doing, I will run it. Sorry, okay. So you can see here what's is going on. Basically, the software automatically has defined different values for all the parameters. You can evaluate the geometry here. You can see all these kind of iteration are evaluated, and the software is evaluating the mass, because we have told to find the minimal value, and the thermal stress, the temperature on the from the thermal analysis. So it can evaluate automatically which is the best. In this case, those ready iterations are not good. At iteration 13, for example, it can be good, but it can go on, and it has found that the optimal values are this one. So we have found, of course later on we can refine it, and we can see also the results for this analysis. And we can find out that from the initial value of 1 kilo, we have reduced it to 984, for example. So let's say this is very small, so I have reduced it about, let's say, 10%, okay, more or less. So what does it mean? It means that you can do this automatically, or let's say the software is doing this automatically. Of course you are designing the parameters, but you can leave the software do this kind of research for you. Okay. So again, this is an R&D tool. It's automated from analysis, in this case from thermal analysis, but you can use static analysis, you can use backlink analysis, and so on. You can reuse each CAD dimension that you have already, because we are in SOLIDWORKS, so you can reuse everything. The restraints are based on sensors, so you can define, for example, the maximum displacement on a static analysis, or the temperature on a given point, or the backlink load factor, whatever you want. And you can also define a continuous range of the parameters. So you don't have to define each different value. You can just define, for example, the thickness from 1 millimeter to 10 millimeter, and the software do the rest. Okay? Let's go on. So to finish, we are late, but I think it's valuable for you. It's something interesting, because I see that more or less you are staying with me. So I think we can finish with simulation premium. I will introduce linear dynamic analysis, and later on the nonlinear analysis. For example, of course, we can show a lot of examples here, but I would like to show you a specific example about earthquakes. In this case, we have a steel structure, and you know probably better than me from structure point of view. Now there are specifics, let's say, specific normatives, specific norms to evaluate which is the response of a steel structure during an earthquake. For this example, of course, I'm in Italy. I've taken the from the website of our ministry of the public works. I've taken this kind of PSD. What is a PSD? It's the power spectral density of an earthquake, and those spectral density, those PSD curves, are specifically for that kind of earthquakes. For example, in Italy, but I'm sure also in your region, in your territory, there are specific ministries that are taking this kind of curves for the designer, for the engineers. Okay. Okay, let's see what we can do in SOLIDWORKS.